Question 1, we're asked which of the following series diverges, okay? So just from looking at this, let's look at question A. So if we do the limit as n approaches infinity for 1 over n plus 1, this is going to become 1 over n squared plus n. So when you put infinity in here, it's going to become an increasingly large number in the bottom. So we already know that this converges to 0. Okay. And then for this equation, n plus 1 and factorial. So just from looking at this, if we take the limit as n approaches infinity for n plus 1, n to infinity, and factorial, this is going to be increasing way faster than this. Because let's say you put in 500 and like a really, really big number. This is going to be way bigger than the top part. So we know that this also converges. Okay. Now, C, we can use the integral test to determine if it converges or diverges. So we're going to do 1 over x natural log of x, okay? Then we're going to do u sub. So u equals natural log of x, du equals 1 over x dx. So we could literally write that as 1 over x to 1 over natural log x. So when we do the u sub, you can replace this because the du has 1 over x in it, it'll cancel it out. So then all we have is 1 over u du. And then this is going to become, the integral of 1 over u is going to be natural log of u plus c. But we have the bounds, I forgot to add. Limit as a approaches infinity, we're going from 2 to a. Okay. So from a to 2. Okay. And then we can plug back in u. So natural log is natural log of x plus c from a to 2. So this is going to be the natural log of a minus, we actually don't need this, minus the natural log of 2. And then limit as a approaches infinity. So this is not going to converge. It's going to be infinity. So it doesn't matter what this is because this is infinity. So we know that that's the answer because it diverges. So C is going to be the answer for that. And then if you look at this one, this grows way faster than the denominator grows way faster than the numerator, so you also know it converges. So yeah, that one is going to be C. Okay. In this question, we're given 3 different series and we're being asked which of them, or do all of them converge? So if we look at this one, this is a P series, it's pretty straightforward. For following the P series test, if P is greater than 1, then converges. And then here we can see P equals 2, so we know that that series converges, okay? Now, if we look at this one, it's also a P series, except here there's no exponent. There is, but it's 1. And given what the P series test says, if P is greater than 0 and less than or equal to 1, then it'll diverge. So because of that, we know this series does not converge. And then for this one, the last one, this is an alternating series because of the -1 to the n. at n. So if you want to know if an alternating series if an alternating series converges, you're going to use this over here and you're going to go as the limit as n approaches infinity, 1 over n. And then you'll see that as you go to infinity here, the denominator is going to get increasingly small. So it's going to go to 0 at one point if it reaches infinity. And by the alternating series test, if the limit as n approaches infinity equals 0, then it'll converge. So based off of this, these two converge, therefore the answer is D. Okay, so question number 3 is about conditional convergence or absolute convergence, right? So consider the following series which the following statements are true. So first let's find if they converge in the first place. So for number 1, this is a alternating series, -1 to the n. I'm going to write this as n to the 1/3. So looking at this, we can see that number 1, it alternates. Number 2, it is decreasing because as n increases, this is going to become bigger in the denominator and the number is going to become smaller and smaller. And if you approach the limit as n approaches infinity of 1 over n to the 1/3, that's going to equal 0. So based on all of these, this will converge. Now, if we want to check if it absolutely converges, we have to do the absolute value of that one, right? So if we do the absolute value of -1 to the n over n to the 1/3, so this is going to become 1 over n to the 1/3. It's not going to alternate anymore between positive and negative. And then here we can just use the p-series test. And since p equals 1/3, that is in between 0, 1/3, and 1. So based off of the p-series test, this converges conditionally. Because when you do the absolute value of that series, it'll diverge. This diverges. So we know that number 1 converges conditionally, okay? Now if we look at number 2, let's do the same test. It is an alternating series. So n to the 3rd, okay? So again, this is going to be, it alternates, it's decreasing, and the limit as n approaches infinity of 1 over n cubed is going to equal 0. Because again, this is growing really rapidly, and the numerator is just 1. And then to find if it converges absolutely, we have to take the absolute value of that. So we're going to do 1 over n cubed. And then again, we'll do p series. P equals 3. So actually p is going to be greater than 1. So that's how we know that this converges due to the p-series test. And since this is the absolute value, this is going to converge absolutely. So neither of them diverge. One of them converges conditionally and the other one absolutely. So the answer is going to be C. Question number 4 is asking about convergence and divergence using different methods of this series. So just by looking at it, it's gonna, these three answer choices are about using a comparison test to a different series. So we're gonna do that. Out of all of these, honestly, this 2 to the n over 3 to the n plus n. Okay, so when you're looking at this in the major scheme of things and you're thinking of infinity and all of that, this isn't really a dominant term, the n, so we can scratch that. Only consider 2 to the n and 3 to the n, right? And we know that this is approximate, not equal, but approximate to 2 over 3 to the n, okay? And that is a geometric series in which r equals 2 over 3. And basically, knowing what we know about geometric series, if r is less than 1, then converges, right? So since r is equal to 2 over 3, that is less than 1, then this geometric series will converge. So out of all of these, it's going to be D, because this is missing the 2 to the n. It's not realistic. This one, just no. It's missing a lot of parts of it, and yeah, this one is probably the most complex one to do. So it's asking which of the following statements is true from all of these. So the first series we're given is -1 to the n of 1 over rad n. Okay, so this is an alternating series, so we can use the alternating series test because it is decreasing and it's alternating, which is pretty obvious. It's going back and forth between positive and negative. So if we do this, we're going to take the limit as n approaches infinity of 1 over n. We'll write this as 1/2. And this is going to equal 0 because this is going to increase really fast and ultimately it's going to converge. So this is wrong. A is wrong. It says it diverges, okay? Now if we look at B, this is another alternating series. It says that this one converges. So let's check. -1 n to the 1, 4 rad n all over 2 plus rad n. Okay. So again, this one alternates and it's decreasing. So when you take the limit as n approaches infinity, do 4 rad n all over 2 plus rad n. So if this approaches infinity, it's going to kind of be like 4 rad infinity over 2 plus rad infinity, right? The 2 doesn't really count. These are going to cancel out to 1, so this equals 4. And the alternating series test says that it only converges if it equals 0. So since it does not equal 0, this series will diverge. So that one's also wrong. Okay. Now let's try question C. So this one, this one is asking us to use a ratio test. So the ratio test says that you have to use a to the n plus 1 or a to the n to find if it converges or diverges. So let's do that for this. This one's going to take a while. So if we do equals 1 of 8 minus n, 6 to the n all over 2 times 4 to the n. Okay, so let's do a to the n plus 1. So we have 8 minus n plus 1. So I'm just going to write that as 9 minus n. 9 minus n all over 6 n plus 1 all over 2 times 4 to the n plus 1. And then we have to divide that by just the original. But if we're dividing, I'm just going to multiply by and switch the top and bottom. Sorry. 8 minus n times 6 to the n. Okay. So if we do this, let's say we multiply those two together. 2 times 4 to the m. And let's say I'm going to bring this up, the 4. So it's going to be 4 negative n minus 1 if I bring that up to the numerator. So let's forget about the 2 for now. That's going to cancel out. The ends are going to cancel out. This is going to become 4 to the negative 1, right? So this 4 is going to cancel, and this 4 is going to stay, but it's not going to have anything over here. And then the 2's are going to cancel out, right? So we have 9 minus n, 6 to the n plus 1, all over 4, 8 minus n, 6 to the n. Now we can simplify this too. So if we do the same logic as to what I just did, apply the same logic, 6n plus 1, and I move that to the top, it's going to be 6 to the negative n. So this will cancel out, and then only 6 to the 1 will stay. So then we can cross that out and cross that out. So now we have 9 minus n all over 6 times 9 minus n all over 4 times 8 minus n. And then we're going to do the absolute value of that because that's what the ratio test asks for. Okay, now if we take the limit as n approaches infinity of this, these are just going to go to infinity, both of them. So these two are going to cancel out, and all we're going to have is 6 over 4. And 6 over 4 is going to simplify to 3 over 2. So that's the limit as n approaches infinity. The ratio test asks that it has to be less than 1. What you get here has to be less than 1, and 3 over 2 is going to be greater than 1. So it'll diverge. For the ratio test, you would have to have less than 1 in order for it to converge. So we know that C is wrong. And then we already know that D is right because it's a lot of work. We already know D is right because we got rid of everything else, but why don't we just do it? So n equals 1. So we have negative 1 to the n of 4 over 9 plus n squared. So again, this alternates and it is decreasing in the denominator. So we can stick to this. Limit as n approaches infinity of 4 over n plus n squared. And then this is going to go to 0 due to the n squared in the bottom. So based on that, since it equals 0, it converges. So the answer is D. Okay, so in this question, we're given this sum, and then we're given that partial sum to 2, starting at 0, of negative 1 to the n plus 1 all over 2n plus 1 factorial. So find the error bound of the alternating series, okay? So if you want to find the alternating series error test tells us that to find the error bound, if they tell you that it starts at n equals 2, you're going to find the error bound at the first omitted term of the series. So if it ends at 2, then we're going to use 3 for the error bound test, okay? So if we plug in negative 1 n plus 1 all over 2n plus 1 factorial, if we plug that in, negative 1, 4 all over 2n plus 1 factorial, here we're going to get 7 factorial, okay? Negative 1 to the 4 is just going to become positive 1. And then 7 factorial is 5040. And then if we simplified that and we made it a decimal, we would get 0.000198. So that's the error bound of the series, okay? Given the error bound, is approximation an underestimate or an overestimate? So the error bound here, it's a positive number. You write it down. The error bound is a positive number, which means that since it's positive, the approximation is going to be less than the actual value. So this means that it's going to be an underestimate. Because basically if it was a negative number, it would be an overestimate because it'd be over the actual value if it was negative. And then this one's kind of a separate question, but it's asking, given the series, this is a series, -1 to the n plus 1 over rad n. Using the alternating series test, what is the least number of terms necessary to approximate the series within 0.001 of the actual value? So they're asking us to find the smallest integer possible, so that this is going to be less than or equal to 0.001, right? So yeah, it's the least number of terms. Okay. So again, we're going to use the first omitted term. So we're going to use 1 over k plus 1 must be, so k is our value for like the least number of terms that you need to approximate the series, okay? So basically what we're going to do, if you move this up to the numerator, then you have to also, divide this by 1. So if I did 1 over 0.01, so we're going to get k plus 1. This doesn't change because I didn't multiply by anything negative. And that's going to become 1,000. Okay. And then if I square this, we're going to get k plus 1 is less than or equal to a million. 1, 2, 3. And then k less than equal to 999. If you minus by 1 here. And yeah, that's going to be the least number of terms necessary to approximate the series within 0.001. So yeah, that's the answer. Given the series, and then they gave us a different series, n equals 1 to the -1, n plus 1 over rad n. Using the alternating series test, which is the least number of terms necessary to approximate the series within plus or minus 0.01 of the actual value, okay? So again, like what I said about the last one, you're going to use the last omitted term in the series to find the error bound, right? So we're looking for a k, and k is going to be the least number of terms that you need to get within 0.001. So if we wrote that, be 1 over k plus 1, because we're using the omitted number, so we have to do plus 1. And then they're saying the least number of terms, so we're going to do less than or equal to 0.01, 0.001, okay? So now all we have to do is simplify this to find the number of terms necessary, okay? So first of all, I want to move this up, but if I move that to the numerator, I'm going to divide this by 1. So we're going to do k plus 1. This is going to move into 1,000. If you do 1 over divided by 0.001, it's going to become 1,000. And then we have to square this. So that's going to be equal to k plus 1. Or equal to million. then minus 1, minus 1. So k is greater than or equal to 999,999. So that's our answer. The least number of terms necessary is going to be 999,999. So yeah, that's all with the partial sums in that part. Okay, so this question gave us the following series. It's n squared all over n cubed plus 1 and to the infinity. And it's asking, use any test to determine if the series converges. State the requirements in which the series must fulfill the requirements in order to apply the test you used. So just looking at this, it would be good to use the integral test because if you do u sub, this would cancel out at one point, and it would be easy to get an answer if we use the integral test. So before I use the test, to make sure that if it fills the requirements. So in order to use the integral test, the series has to be continuous and it has to be decreasing, right? So if we look at this is continuous and it's going to be decreasing because this is a higher power and it's in the denominator, so it's going to get smaller and smaller. The more numbers, the higher the number gets, right? So if we use the integral test, we're going to rewrite as f of x equals x squared all over x cubed plus 1. And then we're going to do the limit as a approaches infinity from 1 to a of x squared all over x cubed plus 1. Now to solve this, we're going to do u sub. So u equals x cubed plus 1. And then we're going to get du equals 3x squared, right? So we're going to do limit as a approaches infinity of 1 to the a of x squared all over u. Then that's going to be, du is going to be du all over 3x squared dx. So these are going to cancel out. You're going to have a 3 left. So you can put the 3 out. So limit as a approaches infinity of 1/3 1 to the a of 1 over u du. So this, the integral of 1 over u is just going to become natural log. So we're going to get 1/3 the natural log of u. Okay. Then u, we're going to sub back x cubed plus 1, so 1/3 x cubed plus 1. And then we're going to evaluate it from 0 to a. And remember, limit as a approaches infinity. Okay. So we're going to plug in 1/3 a cubed plus 1 minus 1/3. Sorry, I forgot the natural log. Natural log of a cubed plus 1 minus 1/3 natural log of 1 cubed plus 1. I don't know why I changed that to 0. Okay. So if we evaluate this as limit as a approaches infinity, we're going to get 1/3 natural log infinity, and that approaches infinity. So just based off that, using the integral test, because the integral x squared over x cubed plus 1 as it approaches infinity 1 to a, that's going to equal infinity. So based off of that, the series is really ugly. The series is going to diverge. Okay, so now that we know that it diverges from the integral test, we use the integral test here. Now it's asking us to use a p-series to determine why the series does or doesn't converge. So we do n equal to 1 of n squared over n cubed plus 1. And let's say we only look at the dominant factors of this series, so plus 1 doesn't really matter. So we're looking at n squared over n cubed. If we simplify that, we're going to get 1 over n, nothing in the bottom. 1 over n is going to have p equals 1. And we know that if p equals 1, then it's going to diverge. But if p is less than 1, it'll converge. So that is how the p-series test proves that this also diverges. So those are two ways, through the integral test and the p-series, that this series diverges. Okay, so this question says, given that a of n equals negative 1 to the n plus 1 all over n plus 1 to the fourth all over 4 to the n. Find the limit as n approaches infinity using the ratio test, and then state whether the series converges or diverges. Okay, so the ratio test states that if you have a to the n, the ratio test is the absolute value a to the n plus 1 all over a to the n. Okay, so if you want to solve for that, you're going to do negative 1 n plus 2 times n plus 2 to the 4 all over 4 to the n plus 1. And then you would divide that, but I'm going to multiply it and then just switch the numerator denominator. So then we're just going to do the normal 1, negative 1 to the n plus 1 all over n plus 1 to the 4. Okay, so now we have to simplify this. So these two, so you have 4 to the n, and then you move this to the numerator, it would be 4 negative n minus 1. So the n's would cancel out and you'd be left with 4 to the negative 1. So this is going to cancel out and you're still going to have 4 in the denominator here. Okay. And then here you have negative 1 to the n plus 2. Again, if we do negative 1 to the n plus 2 and we move this one up, negative 1, negative n minus 1. So we'd be left, the n's cancel out again, and then we have negative 1 to the 1. So this is going to cancel out, and then only negative 1 is going to be there. So right now we have negative 1 to the n plus 2 to the 4 all over 4 n plus 1 to the 4, okay? Again, this is all absolute value. And then we're going to do the limit as n approaches infinity of this, okay? So if this is an absolute value, then that negative 1 is just going to become a 1. So all we have is n plus 2 to the 4 times 4 to the n plus 1 to the 4, okay? Now, if you did limit as n approaches infinity of this, so n plus, if you put infinity in here, since they're both to the fourth, they're both going to equal 1. They're going to cancel each other out. So all we have left is 1 to the 4. So that's going to be the answer. 1 to the 4 is going to be the answer for the ratio test. So that's going to be the limit as n approaches infinity. And from what we know on the ratio test, that if the limit is less than 1, then it'll converge. But if it's greater than 1, it'll diverge. So 1/4 is less than 1. Sorry, my mom came into my room. So yes, we know that the limit as n approaches infinity is going to be 1/4, and 1/4 is less than 1. So therefore, by the ratio test, this is going to converge. Okay, so here we can write that it converges. Okay, so for part B, it's asking if the series in part A converges, does it converge conditionally or absolutely? Show your work. So if we want to know if it converges absolutely, we're going to have to take the absolute value. So if we have -1 to the n plus 1, n plus 1 to the fourth, all over 4 to the n, if we took the absolute value of that, this would go away, and then we would have only n plus 1 to the fourth, all over 4 to the n, which is going to be all positive. And then basically, if we took the limit as n to the infinity of n plus 1 to the 4 over 4 to the n. So this power function, and then this is 4 to the n. So this one is going to grow way rapidly compared to this one. This one also goes to infinity. At one point, it'll reach infinity, but this will reach infinity way faster. So I'm going to say that this is converging to 0 because of how rapidly the denominator increases. It's going to become a really small number that's going to equal 0. So if the absolute value of this function of the series equals 0 and it converges, then that means that it absolutely converges. So no matter what, the series this is gonna converge. And yeah. So this question right here is my investigative task. So forgot to include the text part, but I'll read it out loud. So a bouncy ball is dropping from a height of 10 meters. Here it's dropping from 10 meters and continues to bounce infinitely. After the first bounce, it reaches a height of 5 meters, and then after the third, it reaches a height of 2.5 meters. So the focus of this question is on the total vertical distance of the ball, not the direction that it's moving in, like the positive or negative direction. So again, the ball is starting at 10. Let's say it's on a cliff here, and then it fell off the cliff, and then it went down 10, went back up 5, went down 2.5, okay? So here this graph is about the total, this visual is focused on the total vertical distance of the ball. Okay. So first it's asking, write the series for the vertical distance of the bouncing ball if it infinitely bounces. Write both the recursive and non-recursive form. Okay. So if we look at this ball, see here that there's a pattern. It starts at 10 meters, right? And then when it falls down, it'll fall down 10, and then it'll go to 10 to the 1/2. And then it's going to go up 10 to the 1/2. It'll come back down 10 to the 1/2. 10 to the 1/2. And then again, it's going to become 10 to the 1/2. 1/4 actually, but we're going to write that as squared. And then when it comes back down, it's going to be again 10 to the 1/2 squared. And this is going to continue on and on and on and on. So if you can see the pattern here, if you're confused about this, again, the ball is going up vertically and then it's falling down. So both like the ball ascending and descending are being accounted for because we're talking about the total vertical distance, not the direction that the ball is traveling in, okay? So if we rewrote this, if we simplified it, it's going to be 10 plus 20 to the 1/2 plus 20 to the 1/2 squared. You can see a pattern forming here. And this 10 is kind of screwing everything up, so I'm going to rewrite it. We're going to rewrite it as -10 plus 20 to the 1/2, 0, plus 20 to the 1/2, That's 20 to the 1/2 squared, on and on and on. Because we can redo this because 10 to the 1/2 0, 1/2 of 0 is gonna be 1. So then that would just be 20 minus 10, which is equal to 10. So that's legal. We're allowed to rewrite it like that. So if we say that this is, we're going to have to rewrite this one as a sum, as a series, sorry. So as you can see, we have a 20, and then it's increasing by 1/2 times 1/2 times 1/2 times 1/2. So we could say r equals 1/2, so it's going to be 20 to the 1/2 k. It's a geometric series. Then we're going to write, it's going to be, I want to have more space. Okay. So we have to include the -10, so we're going to have -10 plus series infinity from k equals 0, 20 to the 1/2 of k. So that's going to be how you write it. Okay. And then question B is asking, find the sum to infinity of the geometric series. So B, so now that we know the series, we're going to do -10 infinity k equals 0, 20, 1/2 k. Okay, so since this is a geometric, we're going to use what we know from the geometric series test, and we know that r is going to equal 1/2, and r equals, if r equals 1/2, we know that 1/2 is the absolute value of r is going to be less than 1. So we can apply our rule a1 minus r to find the total sum. And this can only be done for geometric series to find the sum to infinity. So we can use this rule, we know that. So a is 20. So we have 21 minus 1/2. So that's going to equal 20 over 1/2, which is going to equal 40. And we're not going to forget this -10 right here. Bring it down. So now we have 40 minus 10 equals 30. So 30 meters is a total, it's a total vertical distance that the ball is going to travel, going both up and down. So yeah.